In this video, we're going to look at approximating areas under a curve using Riemann sums. Let's suppose that we are in our car, we have our cruise control on, and we are driving for a total of 2 hours, and our velocity is at a constant 60 miles per hour. The displacement, how far I went in those 2 hours, would be the 60 times 2, and that can be represented by the area underneath the curve of velocity being 60. Because objects rarely move at a constant velocity, we're going to extend this idea of the area under the curve to determine the displacement by looking at rectangles. That we're going to build these rectangles. So suppose our velocity is described as t squared, where we're going to go from 0 to 8. So I'm going from 0 to 8. You can see that this is not a straight line, and so I'm going to build rectangles. And I'm going to start out with rectangles of equal distance, so they're the same width. Now, if I have two rectangles, I'll be at two rectangles. My first rectangle will be 4, and my second rectangle will also be 4. So 48 is 4. So its width is 4. And then the height is going to be determined, I'm going to say, at the midpoint. So the halfway mark between 0 and 4 is 2. So the height of my rectangle is going to be my velocity defined at 2. So that's going to be, the height here is going to be 4. T squared is 4. Now the halfway mark between 4 and 8 is 6. So I put 6 into this function, and I end up with a height of being 36. But you can see that I have all of this underestimation in this area, and I have all of this overestimation in this area. So it's not a very good choice to have only two rectangles. So if I do 4 rectangles, then of course I take my total distance from 0 to 8 divided by 4, and each one of these are going to have a width of 2. My height is going to be the midpoint, so this height, so this is the point 7, because that's my midpoint. So my input is 7, and my height is going to be 7 squared. And so the area of this rectangle is going to be the width of 2 and our height of 7 squared. You can see, though, I have a lot of underestimation in this area and a bunch of overestimation in these areas. So let's let my number of rectangles to be 8. So these are all going to have a width of 8. The height is going to be determined right here. So this rectangle would be a width of 1 with a height of 7.5, the quantity squared. I don't have as much of under and estimation, so it looks like it's getting a little bit better. Now this is what it looks like when it's 64. When you have 64, so its width, the width of each one of these would be 8 divided by 64. That would be the width of my rectangle. And then the height would be dependent on which rectangle I'm looking at the midpoint. So for this example, I have one interval, and I have a length of 8. This is my approximation of the displacement, or in other words, the area under the curve. And then I go up to 64. And notice when I get up to 64, there isn't much change between 32 and 64. In fact, there's just a little bit of change between 32, and 64. But notice there's almost no change between 32 and 64. So 64 is a good choice if I'm building rectangles. I have 64 rectangles. Because Riemann sums is looking at summations, we need to have a little bit of refresher about summation notation. This is the lower index. The index summation is the k, that's the variable, so this is called the lower limit of summation. And this number up here is the upper limit of summation. And this 2 of k is the explicit formula. So if I was asked to do this and write it out, what I would be asked to do then is do 2 multiplied by 1, so that's my first k. 2 multiplied by 2, that's when k is 2. 2 multiplied by 3, that's my k is 3. 2 multiplied by 4, and then 2 multiplied by 5, and then be asking me to add up all those numbers. So that's what summation notation does. We can look at our summation notation and say, hey, if I have from I equals 1 to n of some constant, it's just going to be my upper limit multiplied by c. So that's nice. If I have a constant and it has an explicit formula a sub I, my constant can just be pulled out as a multiplier, and then I can just do my a sub I, whatever my explicit formula is. If I have two separate explicit formulas, then I can break it up with an addition between them, or if I have subtraction as well as subtraction. if I have a index where I start with 1 and I stop, say, somewhere along the way, I can then pick up with the same explicit formula at m plus 1 all the way to n. So if there's a reason like, oh, I don't know, if you're doing the summation of k equals 3 to 20 of my a sub I, then I can use this to write this as a summation of k equals 1 to 20 of a sub I, and then I could subtract off whatever pieces I don't want. And there's going to be a reason why I'm going to do this. So I'm going to start is equal to k equals 1 to 2. I'm going to end at 2, so I'm going to pull off the first and second because I'm starting here at 3. Similarly, if this would have been 4, then I would have gone to 3. And this is a sub I. There's going to be a reason why I do this. So the reason why I do that is here. Now, we have these sums. If I'm summing up from I equals 1 to n of I can use this formula. I squared, I can use this formula. I cubed, I can use this formula. And I have one for the constants, which we knew from before. I equals 1 to n of my constant is just going to be n times my constant. So I can use those formulas down when I want to do these evaluations versus doing the writing out of each and every term. If I'm trying to figure out what the summation notation would be, if I'm giving a string of numbers that are being added together, I'm going to figure out what my explicit or closed formula is. So I'd have 4, 5, 6, 7, 8, and 9 if it was a sequence. If it was a sequence, I'd try to figure out what I have as a sequence. And I can see as I move from 4 to 5, I'm doing a plus 1. So this is plus 1, this is plus 1. And so my closed formula, what I think is a sub n, is equal to, I have an a naught, and then I have plus my n times d. My n being the independent, or k if you want, or I if you will, and then my d being my difference. And this is for an arithmetic sequence. And I know it's arithmetic because I'm going up by the same amount, or if I'm going down by the same amount, then I have an arithmetic sequence. So my a sub naught is always going to be my a sub naught, is always going to be my a sub 1 minus my difference. So in this case, my a sub naught is going to be 4 minus 1, which is 3. So my closed formula is going to be my a sub naught, which is 3, plus n times 1. Now I can check this by putting in n being 1, I get 4, n being 2, I get 5, n being 3, I get 6. So where I am now is building the summation notation. So I have the summation of n equals 1, 2, and I have 1, 2, 3, 4, 5, 6 terms of my a sub naught, which is 3, plus my n times d, so plus like that. And that's my sigma notation. In this case, what I've got is this goes up by 5, and this one is going up by, 5. Oh, so that's nice. So I know that my closed formula a sub n is going to be my a sub naught plus n times d. My d happens to be 3 or 5, and my a sub naught is going to be 3 minus 5, which gives me a negative 2. So my closed formula a sub n is going to be negative 2 plus n times 5. So I'm going to write it as 5n. So 5n. However, I don't know how many terms. I don't know where it stops, so I have to figure that out. And the way I figure that out is I say negative 2 plus 5n is equal to 63. So 5n is equal to 65. N is equal to, I don't know. What is that? 5 goes into 6 one time, leaving me 15, so 13. So this summation notation is n equals 1. And I could use k, I could use I, I'm using n, I could use any value I want for the variable. I usually use k, I, or n for these summation notations. 1 to 13 of my closed formula, which is negative 2 plus 5n. All right, now let's take a look at this one. This one is different because I am not going up by the same amount. What is happening, I have 1 times 2, 2 times 3, 3 times 4, 49 times 50. What it looks like is that this is 1 over n plus 1 if I put 1 in. So let's check to see if that works. If I put 1 in here, I get 1 and 2. If I put 2 in here, I get 2 and then 3. Oh, that looks like it's probably my sequence. So my closed formula, n equals 1 to, I don't know when I stop, of 1 over n plus 1. Well, if this is 1, this is 2, this is 3, this must be 49. So that is my closed formula. Now, if I want to evaluate my summation notation, I can rewrite this as the summation of k equals 1 to 6 of 2k plus the summation of k equals 1 to 6 of 1. The reason I'm doing that is I can now pull out the 2, and then k equals 1 to 6 of k. And the second part is, I can use this formula right up here. That's just going to be 1 times 6. So this is just going to be 1 times 6. Now this, I have a formula for that too. I can add them all up if I want, or I can use this formula right here, which my upper bound is 6. So it'll be 6 plus 1 divided by 2. So this becomes 2, and then 6 plus 1 divided by 2. And the reason I have a 2 is because this 2 is that 2. And of course I have plus 6. Now you can see that this 2 and this 2 will cancel. So I'm left with 6 times 7, which is 42, plus 6 more, so my sum is 48. Or I could have just wrote them all out. That would have been fine as well. I don't have any cool little formula for this one, so I'm just going to have to do the summation. So I'm going to put in k equals 0. So I have the sine of 0. It's my first term. Then I have the sine of 1 pi over 2. And then I have the sine of 3 pi over 2. Oh, no, I guess I should have 2 pi over 2. I don't know why I just jumped right over that one. So 2 pi over 2. And then I have the plus the sine of 3 pi over 2. And then I have plus the sine of 4 pi over 2. Now we know the sine of 0 is 0, the sine of pi is 0, the sine of 2 pi is 0. So I end up with the sine of pi over 2, which is 1, minus the sine of 3 pi over 2, which is the negative 1. That's why it's a minus 1, so my answer is 0. Let's take a look at my last one. Now, I need to be able to use my formulas up above, as I need to be able to have the start at j equals 1. So I'm going to put in 0. So I put in 0, so I have 0 squared plus 3 times 0 minus 1 plus, now I have j equals 0, or excuse me, 1, j equals 1. So now I can start out with 1 to 40 of the j squared plus 3j minus 1, which gives me negative 1 plus the summation of j equals 1 to 40 of j squared plus 3, the summation of j equals 1 to 40 of j, and then minus the summation of j equals 1 to 40 of 1. So once again, I have, this is going to be equal to negative 1. I'm going to go up here and find the equation for j squared, which is the upper index, and then plus 1, and then 2, the upper index plus 1. So this is going to be equal to my upper index, which is 40, 40 plus 1, 2 times 40 plus 1, divided by 6, I believe. So let me go back up and check. Yep, so it's divided by 6. And then, so that's that one. And then I'm going to have this one, which is going to be plus 3. And we know that this is the 40 plus 1 divided by 2. And then minus 40 times 1. And that would be that last one is there. Okay, whatever that equals. It's just a nice refresher of our summation notation. Now, if I'm asked to approximate the areas by Riemann sums, I have multiple choices. We can have the left, the right, and the middle. Right now, we're just going to focus on the left and right. So what I have to do is I want to take my interval from A to B and break it up into the exact same size to make it easy to do the Riemann sums. So I want these changes, delta x, to be the same size. So I start out with x naught being A and x sub n being B. So what we do then to make sure that we are in the same number of intervals is we take our length of our interval, which is A to B, whatever that length is, we divide it by however many pieces we want, and that's going to give us the delta x. So our delta x is going to be equal to, the length from A to B, so B minus A divided by the number of intervals that I want. And that's going to tell me how wide my base of each one of my rectangles are going to be. And then, of course, I have the height. The height is going to be determined on whatever my input is at that moment. What do I mean by that? Well, let's take a look at this example. If we have n number of pieces and we are doing the left endpoints, then I start out with x sub naught being A. So that is the height that I'd put in. I would put A into my original function, and that would be the height. That is this piece of it. And then I'd multiply it by the width, which is delta x. Remember, delta x is going to be the B minus A divided by n. So that's my width of my rectangle. My next endpoint would be my A plus my delta x. So that's going to be my next endpoint. Whatever that value is, I put into my original function, and that's going to give me my height. And then I have my next one and next one and next one. This is the left endpoints. If I'm doing the right endpoints, then I start out at, for the right endpoints, I start out at not x at A, I start out with my delta x plus A. That would be my first height. And then I go, in this case, I end at B. So the difference between the left endpoint and the right endpoint is that when I'm doing the left endpoint, I start with A and I end with one value less than B. The right endpoint, I start at one value after A and I end at B as being my last height. So you can see this is the left endpoint of that curve and this is the right endpoint of that curve. We'll do the midpoints later in the next, well, actually we'll do it in Calc 2. So the Riemann sum is going to be the summation of each height, that's what this notation is, each height multiplied by the delta x. So if I want to figure out what my Riemann sum limit would be, I would recommend you figure out what delta x is first, and then decide if you want to do left, right, or midpoint. Well, we're going to wait for the midpoint, so let me get rid of the midpoint. We're going to wait for midpoint until Calc 2. So if I want to look at from 2x squared from 1 to 6 with 5 intervals, the first thing I'm going to do is find my delta x. My delta x is going to be 6 minus 1 divided by 5. That tells me my delta x, or the width of each one of my rectangles, is going to be 5 over 5, so in other words, 5. Now, I want to find my height. My grid points are going to be x sub naught being my first one, starting at 1, because I start at 1. Then my next one is going to be my x sub 1. Here, the reason I got this x sub 1, x sub 1 is going to be x sub naught plus my delta x multiplied by 1. Then my x sub 2 is going to be my x sub naught plus delta x multiplied by 2. My x sub 3 is going to be x sub naught plus delta x multiplied by 3, and etc. So that's how I get my x sub 1, x sub 2, x sub 3. So this is what it looks like. this is my Riemann sum. Here is my width. And my height on the left-hand side is I'm going to put in 1 into my original function, which gives me 2. So 1 times 2, that's that height. This 8 comes from the fact that we have this value. It has a width of 1. I put in 2 into my original function. Remember what my original function is. My original function is 2x squared. So this is 2x squared. So this is 1 times, I put 1 in there because I'm doing my left-hand side. So 1 multiplied by 2, that's why I have a 2 there. This is my width, so delta x, which is 1, multiplied by 2, and then 2 squared, that's why that's an 8. The 32 is my delta x, which is 1, and my f of, now what I'm putting in is 3, which gives me 2 times 3 squared. So 2 times 3 squared should give me not 32. That should give me 9 times 2, which is 18. So that's not right. And then I put in my next one, which is 4, and etc. So my approximate area with the Riemann sum would be the summation of these numbers. Now, if I'm doing it on the other side, so now I'm doing my right-hand side, this area would be still delta x multiplied by, this is still 2x squared. So it is squared, right? Yes, okay, cool. All right, so this time my height here, that rectangle is going to be 2 multiplied by 2 squared. This rectangle is going to be my delta x multiplied by 2 and then 3 squared. This rectangle is going to be delta x and then 2 multiplied by 4 squared, and etc. So then, of course, we have this next area, and we get all the way to the right-hand side. So we've either underestimated it or we've overestimated it. Now let's take a look at my last example. And what I want you to do is ignore all of this. That's all just, I'm not sure why that's there. So let's just get rid of all that. Pretend that's not there. Pretend that's not there. And if you're following along on the notes, let's pretend that that's not there as well. I don't know why it's there. It's not right. I don't know. COVID, we all lose our minds. I don't know. Whatever. Anyways, let's go here. So the first thing I'm going to do, here's my graph, and I'm asked to go from negative pi halves to pi halves. So that means I need to go down here. Well, actually, that's a terrible drawing. This is going to be a terrible drawing, so you're just going to have to just kind of close your eyes and pretend that that's nice like that. So this is negative pi halves, and this is pi halves. So I have to figure out what my delta x is. So my delta x is going to be pi halves minus a negative pi halves divided by 6. So this is going to be pi halves plus pi halves, which is pi. So it's pi divided by 6. So this is my starting point. This is my x naught, which is pi over 2. Now I know that I'm going to have 6 in here. I'm going to have 6 intervals. So I'm going to have 1, 2, 3, 4, 5, 6. Still not drawn well. Let's make this 5 and 6. So I have to figure out what my x sub 1 is. Well, my x sub 1 is going to be x naught plus delta x. My x sub 2, so this is x1, this is x2. My x2 is going to be x sub naught plus 2 times delta x, and etc. So let's just do the first one. Let's do x sub 1, which is negative pi halves plus pi over 6. This is going to be a negative, same common denominator, negative 3 pi over 6 plus pi over 6 gives me negative 2 pi over 6, which is negative 3 pi, or negative pi over 3. Negative pi over 3. So this is equal to negative pi over 3. Now I would do the next one, which is x sub 2. This is going to be pi over 2 plus 2 times pi over 6. And we're going to find this to be negative pi over 6. And then 0. And then pi over 6. Then pi over 3. That's just what it's all going to work out to be. Now, if we do the left side Riemann sum, then I start out with x sub naught. So my first one is going to be this delta x multiplied by the cosine, because I have a cosine, of pi over 2, because that is my left value. This rectangle is going to be this height times this delta x. So that's that rectangle. So plus my delta x. Now we know delta x is pi. It's pi over 6. So this is going to be pi over 6. And this one's going to be pi over 6 times the cosine of pi, negative pi over 3. And this should be a negative pi over 2. My next one is going to be this height and that delta x. So it's going to be plus pi over 6, the cosine of negative pi over 6. And then my next one is going to be this width and this height. So that's going to be plus pi over 6, the cosine of 0. And now I'm going to go back to this color again. So this height and this width. So this is going to be pi over 6, the cosine of pi over 6. And of course, my last one is going to be this one, which is pi over 6, the cosine of pi over 6. And then I'm going to add all of those up. And then whatever that is going to give me the approximate area with the left side rule. Now, if I'm doing the right side rule, then what ends up happening is my first one is not going to be this. So I'm going to go ahead and erase this one. If I'm doing the right side rule, I'm going to end up with my last height, which is, of course, this height there. And so it'd be pi over 2. So I start, this is my last height. So it's pi over 2 would be my last height. And it's going to look something like this. So let me erase all of this. And now we're going to use the right side. So my first one would be this height. My second one would be this height. My third one would be this height. My fourth one would be this height. My fifth one would be this height. And of course, my last one would be this height. So for this one, because of symmetry, it's going to get the same answer either way. And that, as you know, that if I would have chose my number of intervals to be larger than 6, I would have a better estimation of the area under the curve. And that is Riemann sums. And I don't know why. I don't know what happened there, why that's all messed up. But anyways, that's it, Riemann sums.